Let's get started. So today we're going to start the new chapter on integral calculus. So this chapter will continue for the rest of this semester and next semester in Math161. Okay. So that means the last lecture for this year will just continue straight with the first lecture for next year. Okay, just continues from there, if you make it. Okay. Yeah. The first bit is going to be on antiderivatives. Okay, this is going to be the starting for integral calculus. It's kind of like in between the two chapters, from differential to integral. Next week, we're going to start integral calculus proper, and that's where all of the proofs and theorems are going to come in. Okay, so I explained it last time, how the proofs will be set up for the tests and exams. So this week, no proofs or anything, just calculations. Next week and the remaining weeks, pretty much half proofs, half calculations. Okay, so the antiderivative, what is that? How do we use it? So consider the following chain of functions. So we start with the function f. We know that from f, we can get ourselves f prime by doing the derivative, right? D by dx. If I give you f, you can give me f prime. So d by dx. Then f prime, if we apply d by dx again, we just get f double prime, and so on. So we get a chain like this. Okay, so you can go to f triple prime. Okay, and we can continue that for however many derivatives we want. Now, the idea for the antiderivative is very simple. The question is, this chain is going to the right. Can we go to the left? Okay, that's the whole idea for antiderivatives. So the idea, d by dx, the derivative operation, can take us down the chain to the right. Okay, so the question is, given a function, let's say f prime, can we go backwards and go to f? Okay. So question, can we go left? Okay. Is there a way to undo the derivative action and go backwards? So f to f prime, that is the derivative. Can we go backwards from f prime to f, undoing the derivative, or in other words, doing the antiderivative? Right? It's the opposite. So the answer, yes, with a little star. We'll get to that later. We can use the antiderivative. Okay, to undo the derivative operation. Okay, and there's a little star on yes. So technically possible, but whether you can write the function down or not, that's another story. Okay, and we'll see later on examples of functions where the antiderivative, right, going left, does exist. Mathematically it exists, but you actually can't write it down. There's no way to do that. Very interesting. You'll see that later on when we go to integral functions, but they are functions that technically exist, but you can't write them down. Okay, very strange, but we'll get to that later. Okay, let's start off with a very simple example just to get the idea, and then we'll look at the more general cases. Okay, so given f of x equals x squared, can we find a function capital F of x such that. And now we want to go left. So instead of from f to f prime using the derivative, we want to go backwards to this capital F. So here we have f to f prime. That's very easy. We've done lots of examples like that. But now the question is, can we go the other way to capital F? Okay. Now from this capital F, we can go to the right. That's very easy. Right, so that still works. Okay, so this gives us the definition for capital F. From little f to capital F, that is the antiderivative we want to work out. But we can go a bit backwards because we know that from capital F to little f is just the normal derivative. So we want to find capital F such that capital F prime gives us back little f. Okay. So we're just taking a step to the right there by doing the derivative. Okay, so what can we do? We want to find this function, capital F, such that when we do the derivative on this new function, we get back this old function, x squared. Okay, any ideas on what we can do? Yeah, think about it. So we want some function, whatever it might look like. When we do the derivative, we get back x squared. So we know how to do the derivative. So work backwards. What is this capital F function? So that when we do the derivative, a power rule thing, we get back to x squared. Sorry? We want to reverse it. So what would the function look like? Sorry?
1 of the square.
Yeah, good. And you can get,
That's the power points. Well done. Student number there.
yeah, 1 over 3, x to the 3. That works. So here we have f of x equals 1 over 3, x to the 3. And the nice thing is, we can check. We do the derivative. If it gives us back the function, then we know it's the antiderivative. So let's do the derivative here. So to do the derivative, we take the exponent down and subtract 1. So we've got x cubed. So taking the exponent down, we get 3 over 3, which is just 1. Taking away 1 from the exponent gives us 2. That's what we wanted. So here, if we do the derivative, we get f prime is going to be 3 over 3, x to the 3 minus 1. So just writing everything out on how we do that. This is x squared, which is what we wanted. Now, the important thing is, this isn't the only answer. What happens if we choose something like this? Let's say we have 1/3 x cubed plus 2. What's the derivative of this function? It's also x squared. So it also counts as an antiderivative. So here, f prime of x is also x squared. Okay, so we got 2 solutions, right? Both of them satisfy the property that if we do the derivative, we get the function that we want. Now we could also do something like this. Okay, 1/3 x cubed plus 37. That would also work. In fact, we can take this 1/3 x cubed, add any constant to it, and that will be another antiderivative. So, very important. The antiderivative I'll put the in quotes because it's not the antiderivative because there's more than one. So the antiderivative of f is any function capital F of x, but we can also add any constant. So plus c, such that if we take the derivative of this whole thing, that plus c just goes away because of the derivative. And this must give us back little f of x. Okay, so we don't say the antiderivative. We say instead a family of antiderivatives. So for every constant plus c that you can think of, you get another solution to the problem. Okay, so it's not the antiderivative. We say that it's a family of antiderivatives. So this collection of functions f of x plus c. Okay, so we have a whole set of functions. For any c, you get another antiderivative, is called a family of antiderivatives. So that's the mathematical name we give to the set of functions, capital F. All right. Any questions so far? Okay, so the whole idea is instead of going to the right here using the derivative, I give you this function f at the start there. Instead of going to the right, we now want to go to the left. So you can add here, there's capital F with d by dx. Okay. So that's the notation we're going to use, capital F for little f. If we're looking for the antiderivative of some function g, then we use capital G. That's just the typical notation. Okay, we use the capital. Okay, and then given that capital F over there, we can go further left using the antiderivative. Okay, and I need my notes back. Now, whatever page you're on, the next page, please leave that whole page blank. Okay, so wherever you are on that page, just turn over to the next page. And then at the top there, write table of antiderivatives. So right at the top in big writing, table of antiderivatives. Okay, please make sure that you start on a new page. There will be a lot to write. Okay, so don't just carry on writing from wherever you are. Okay, so we're going to add to this table a little bit today with a few antiderivatives that you need to learn. These you will have to memorize. That is just university life. I can't help you with that. Okay. So you're going to have two tables now in your book, very, very important tables. The table of derivatives that we finished last semester. Okay, we had all of that there. Now over here, we have the table of antiderivatives. They are going to look very similar. Do not mix them up. If you mix them up, you're going to have a very, very bad time this semester. Okay. You will need to memorize both of them in your head and keep them separate. Okay. And you'll see in a little bit where the confusion comes from. Please do not get confused with this. Okay, so the first thing, we have little f of x, okay, on the left, right, the left side of the table. So for the table of derivatives, we had f and f prime. Now we're going to have f and capital F. Okay. We're going to add a few of these antiderivatives here. So first, it will be x to the n, okay, for some power n. For the derivative, we took the n down, multiplied it, and subtracted 1. For the antiderivative, we are going to undo this process, exactly the same as what we did for here. Okay, so think about the process. We multiplied by n and subtracted 1. That was the order of the operations. Now we're going to go backwards. How do we do that? We add 1 to the exponent and then divide. You see how it's the opposite ordering? Okay. So for the antiderivative, it will be 1 over n plus 1, x to the n plus 1, and always plus c. Always. If you do not put the plus c, you lose half the marks for whatever question that is. Okay. So whenever I ask for the antiderivative or the family of antiderivatives, it's whatever it is, plus c. Okay. And you're going to hear me say that a whole lot this semester. Something, something plus c. Something, something plus c. Okay. Okay, so that's the first one. However, this only works if n is not minus 1. Okay, so please put that condition there. Why? Well, look at that right-hand side. If n is minus 1, we're dividing by 0. We can't do that. So that special case of n being minus 1, we're going to do that separately. Okay, so on the next line here, we have x to the minus 1, or just 1 over x. Okay, and we want to now undo the process of the derivative, right? So the question is, which function, when we do the derivative, gives us 1 over x? Yeah? The natural log, right? We did that for the inverse functions. So the derivative of the natural log gives us 1 over x. So the antiderivative of 1 over x is the natural log. It always goes back and forth like that. So here we have the natural log of x plus c. Again, every time you write it down, plus c. Now, see, this is where it starts getting confusing between the two tables. So on the one table for the derivatives, it was the derivative of the natural log is 1 over x. For this table, the antiderivative of 1 over x is the natural log. Later on, we're going to put the natural log on this side. And now we start getting mixed up with the two tables. Because on the one table, we have the derivative of the natural log is 1 over x. The antiderivative of the natural log, don't write this, but it will be x times the natural log of x minus x. Okay. Now you need to think about what goes where now, right? Okay, don't write that down. We'll get that later, but I'm just telling you, right? It's going to get pretty confusing. Okay, next we have the sine of x. Okay, and now again, we just think about this. This is what we want the answer to be when we do the derivative. So the derivative of what gives us sine x? Not cos. Careful. The derivative of cos is minus sine. So the actual answer is minus cos. Okay. And now again, some more confusion. The derivative of sine is cos. The antiderivative of sine is minus cos. Now, when you get to the test and the exams, the derivatives and the antiderivatives are all going to be mixed up all together. Okay? So some problems you have to do the derivatives, other problems the antiderivatives. That minus sign, you better be very careful about where it goes. So if the question says antiderivative, you need to think, okay, that's the antiderivative table. If the question says derivative, you then need to think of the derivative table. And there's a minus sign difference between the two. Okay. So again, please keep in mind, where does the minus go? What problem am I dealing with? Next one, you can guess it. Cos. We go back. The derivative of what gives cos? Sine. And again, the confusing part is that the derivative of cos is minus sine. Again, there's that minus difference between the two tables. You can't mix them up. Okay. Okay, a few more trig functions. So this won't be the full table. This is just a couple to get started. Sec squared. Tan. The derivative of tan gives us sec squared. So the antiderivative of sec squared is tan. Yeah, you get the idea. Okay, then we have cosec squared. Again, this is where that minus sign comes in. So what is the derivative of cotan? Remember, the derivative of tan was sec squared. The derivative of cotan was minus cosec squared. So again, there's that minus. So the antiderivative of cosec squared is minus cotan. Okay. So wherever the minus was for the derivatives is now the opposite for the antiderivatives. Okay. And then another 2 again with that minus sign. We have sec tan. Okay, the derivative of what is sec tan? Sec, good. So no minus signs there to worry about. But then the next one, that's where the minus is. That is cosec x cotan. What's this one? It's the co, right? It always comes in pairs, right? Sine, cosine, sec, cosec. So that will be cosec, but with the minus sign. Okay. Okay, and that comes with the minus. You can see the pattern here. So cosine, the co-function with the minus, cotan, co with the minus, cosec, again, co with the minus. Yeah, that's how you remember it. And then for the derivative table, it was the opposite. Okay. Okay, one more to add. So we have e to the kx. Okay. Again, we want to do the opposite of the derivative. So if we had the derivative of e to the 2x, by the chain rule, you take the 2 down and you multiply it. If we're doing the opposite now, you don't multiply by k, you divide by k. So this will be 1 over k e to the kx. Okay. And later on, we're going to extend this table. Remember the antiderivative here for the hyperbolic trig functions, the inverse trig functions, all of that stuff that you had in the previous table, you now put in the new table with the antiderivatives. Okay. So you're going to complete the table with that. Okay. So the next thing after this, when we did the derivative table, we did e to the x, and then we did the cos hyperbolic, sine hyperbolic. You're going to add that now. Okay, so cos hyperbolic, sine hyperbolic, all of those, and then the inverse trig functions. You're going to add that. Okay, I think that should take the rest of the page. Please add that for homework. Okay, the rest of those. Yeah.
What if you have an exponential module? So like a to the x.
A to the x. I did mention this when we did the e. We do not deal with that. Yeah. So just like we had the derivative of a to the x, and we said we're only going to work with e as the base. It was long ago. Same thing here. We are only going to work with e as the base. Okay. Some properties of the antiderivative. There's only 2 main properties that we need to go through. The first one is the sum or difference of functions. Okay. Now there's only 2. You might think that's a good thing that there's only 2. We'll see that's actually a very bad thing. Okay. So sum or difference, if we have f of x plus or minus g of x, and now we're looking for the antiderivative not of an individual function, but a sum of functions. The nice thing is If we have a sum or a difference, we can look at each one individually. So the antiderivative of the sum is the sum of the antiderivatives. So we can write this as capital F of x plus or minus capital G of x, and again plus c, just to be safe. Okay, so given little f and little g, if it's a sum, we can just look at each one individually and do the antiderivative. Okay. And then number 2, the constant multiple. Okay, let's say we have some k times f of x. We want to find the antiderivative of this. Very easy. It's just k times the antiderivative of f. Plus c. Okay, again, when in doubt, put plus c. Okay, now, like I said, you might think this is very nice. There's only 2 properties to learn. However, this makes things very, very difficult for us, because when we looked at derivatives way back when, there was the sum and difference rule, we had the constant multiple rule, we had the product rule, chain rule, quotient rule. All of those helped us find the derivative. If I gave you a product, you don't even have to think about it, product rule. If I gave you a composition, you don't have to think about it, chain rule. Now, for antiderivatives, if I give you a function x times sine x, the derivative, very easy. The antiderivative, we will only figure out how to do that middle of next semester. It's actually very difficult in general to find the antiderivative. The reason is there's only 2 properties that we can use. The rest is case by case. Okay. So if I give you some function, again, like x sine x or x squared e to the x, you have to do all of them case by case. There's no rule for a given function to the antiderivative. Yeah. So big warning sign. There are no additional rules or properties to help us find the antiderivative. So if I give you a product of 2 functions, there's no antiderivative product rule. If I give you a quotient of 2 functions, there is no antiderivative quotient rule. You have to take every problem case by case. Okay, we have to take every problem case by case. And that's what's going to be pretty much the whole of next year, semester 1, looking at all the cases for the different problems. So if you have a function and you times it by x, that will be case 1. There will be something to do there. If you have a function and it's composed with something else, that will be another case. If it's a trig function, that's a 3rd case. If it's 1 over something, that's a 4th case. And it just goes on, and you have to learn all of them, unfortunately. Okay, so please put a big warning sign here. Finding these antiderivatives in general will not be easy. Okay, just as an example, let's say we have f of x equals e to the x squared. Very simple looking function. However, the antiderivative, we actually can't write it down. Okay, there's no way to write down the antiderivative using the functions that we know. So square roots, trig functions, exponentials, logarithms, you can think of whatever function you like. You cannot write down the antiderivative. Mathematically, it exists, right? You cannot write it down. So here, f of x equals something. Okay, and as we go through the problems, you will need to identify, can you actually work it out? before you start calculating. Okay. Now that we will only deal with next semester. You don't need to worry about that here. So all of the problems for this semester, very straightforward, easy to do. Next semester, you get things like this and worse, and you need to figure out, okay, can I actually answer this? Before you spend 10 minutes trying to work it out. Another example. Okay, sine of x squared. Derivative of this, very easy, chain rule. Antiderivative, you can't even write it down. Again, capital F of x. No clue how to write that down. No one knows. Okay, so instead, these antiderivatives are written down using integral functions. Okay. We will look at that in a couple weeks. Just a quick show of hands. Who's doing electrical engineering? Okay, quite a few of you. You will be seeing that a whole lot. Okay, so if you do want to change your degree, you can come to my office. I got some forms for you. But yeah, integral functions, you will see that all the way from next year until you graduate. You're going to be seeing those. So derivatives and integrals with those functions, you'll see that come up quite a lot. Yeah. So especially the electrical engineers, the others you'll see a little bit, but not as much as the electrical engineers. Okay, let's have a look at some examples. Okay, quiet down, please. Okay, you can talk about your life choices afterwards. Okay, so examples. Number 1. Yeah. Now, all of these examples, they may look difficult. So some of them are designed to look a bit tricky and so on. However, all of them will be of this form here from the table. Okay. So there's no other calculation that you need to do except for look at the problem, look at the table, write down the answer. Okay, all of them. If you think it looks too difficult, you just rewrite it a little bit. And again, look at the table, write down the answer. Okay. So, number 1, we have f of x is equal to minus 3 over x cubed. Again, you look at it, look at the table, write down the answer. Now here we have something over x cubed. We go to our table. Okay, here we have 1 over x. That's not helpful. Okay, it's not in the table. Do we give up? No. We make it look like something that's here. We can make it look like that first thing, x to the n, for the nice case of n being minus 3. Okay, so just because it's in the bottom doesn't mean it's not that case 1 of x to the n. It just happens that this n is negative. So here we can write this as minus 3x to the minus 3. Now we look at this. This is now x to the n. We can just follow the rules. So what do? We look at the exponent. We plus 1. That gives us minus 2. And divide. Good. So that will be 3 over 2x to the minus 2. You can leave it like that. You do not need to rewrite it as 1 over x squared. Okay. X to the minus 2, that's fine. Yeah? So this was minus 3 divided by minus 2. So it's just 3 over 2. Okay. What are we missing? Plus C. Yeah. That's the difference between getting 2 out of 2 and 1 out of 2. for each one. If you miss plus C on all three, minus 3. Okay. Please do not forget the plus C. The reason is later on that plus C will become very important. For now, it's just something you need to add on, but later on that plus C will actually have some value. It'll be like 2 or 3 or something, depending on the problem. But if you don't write the plus C, then you're missing out on that extra term. Okay, so always just put the plus C. Okay, number 2. F of x is equal to 3 over 2 root x. Again, you look at it. Okay, we got this root here. You go to the table. You look for root x. Okay, we can't see that anywhere. What do? Sorry?
Something we have
Exactly. And how can we do that?
changing to
Perfect. We can make it look like that first case. Okay, so again, if it doesn't look like it's from the table, you do a little bit of work, and then it is something from the table. So this will be 3 over 2 x to the half. Everyone clear on that? Yeah. So, same thing as before. Add 1 to the exponent. That will give us 3 over 2. Then we need to divide by 3 over 2. That will be 2 over 3. We got on, and then plus C. Good. So this will be 3 over 2 from the front times. We had the 3 over 2 in the exponent. We have to divide by 3 over 2. So that was the 2 over 3 plus C. And then we see those fractions there cancel. So this will just be x to the 3 over 2 plus C. And the nice thing is, for all of these problems, you can check your answer right away. What's the derivative of x to the 3 over 2? The derivative is 3 over 2 x to the half, which is what we started with. So you can always go backwards, check your answer, and you know it's correct before I even mark it. And that's true for whatever I give you. You can always check it by taking the derivative and seeing if it matches what we started with. Okay. Number 3. So we got x squared minus 2x plus 1. Now we know from the sum or difference rule that we can do each one individually. So it doesn't matter if it's something plus something plus something. You look at each one and then just put the answer. So let's ignore everything except for the first one. X squared, what does that become? Add 1 to the exponent, makes it 3. Divide by that, so 1/3. And then we go to the next one. So minus 2x, add 1 to the exponent. There's an invisible 1 there, so that will be x squared. Divide by the 2, so it's minus x squared. And then the 1, x, because the derivative of x is 1. And then plus C. Good. And again, we can check. We do the derivative. The 3 comes down, cancels that. So that will be x squared. Good. Next one, the 2 comes down, so we have 2x. That's fine. Derivative of x, that's 1. Derivative of C, that's 0. We know we got the marks already. Okay. Number 4. F of x equals root x plus 1 over root x. Okay, again, the root function, that's not in the table, but we can write that as an exponent. So we have this being x to the half and x to the minus 1/2 because it's at the bottom. Yeah. Same game, add 1 to the exponent, divide. So the first one, a half plus 1 is 3 over 2. Divide by that, you swap it over, so it will be 2 over 3. Okay, next one, minus a half. Add 1, that becomes a half. Dividing by a half is timesing by 2. So it's plus 2x to the half. and plus C. Okay. Any questions so far? We're good. Okay, something a little bit more tricky, but not too bad. Sine squared x. Okay, so we look at the function sine squared. We go to our table. Okay, well, it's not here. What do? We make it look like something that is here. So the functions that are here, sec squared, cosec squared, none of those are going to help because we're looking at sine. So it's between these two. Can we take sine squared and make it something with sine or cosine? What can we do? What's that? Sound like you had some idea?
We did sign.
No. So they suggested sine x times sine x. Remember what I said about the rules. There's no product rule for antiderivatives. So if you write this as a product, you're just as lost as the original function. Because if it's a product, you can't work with it. Yeah. How about an extra 3 points for the next quiz? Maybe that will help get things going. Yeah.
Let me see, 1/, the second squared or the
You could try change it to cosec squared, but you're just making things more difficult. Remember, sine and cosine is always easier to work with than the other ones, so don't make things more difficult. What was that?
Could you also say sine squared x plus 1 squared is 1 and 1 squared?
You could do that, but then you're just replacing sine squared with cos squared. It's same difficulty. But good thinking, very close. Okay, well, let's make it 4 points. Maybe that will help. Eventually, we'll get to 10 out of 10, and you don't have to write next week. Okay, 4 points if you yeah.
No, try dividing yourself.
What does that mean?
1 squared.
1 minus cos squared. Again, we kind of stuck with the cos squared. Yeah. 2. No. Yeah, last problem for today. Okay, let's 5 points. Let's say 5 points. I mean, you can just guess. It's 5 points. I'm not taking points away if you get it wrong. Yeah. Sorry. Yeah.
How does that? No, what you can yeah. Oh, Johnson. You're skipping steps. How did you get that? Googling things. So you said half tense. Where did that come? Yes. Wait, sorry. So you then go. Yeah. Okay.
I'll check with them and then I'll make 6 points. Okay.
IX minus
Hey, no, you're doing complex functions. No, we don't want that. That's scary. No. Okay. 6 points. Great. That's you get better. Yep. But that change will bring up problems. But let's try. Yeah, hold on. So, when other students said the thing about the sine squared plus cos squared, when I said that's almost right, we can use trig identities. We know a bunch of them. So on the side here, let's list a couple. So sine squared plus cos squared is 1, right? So we can go between sine squared and cos squared, but we're just swapping sine squared for cos squared. Doesn't really help. We need to do something else. But we know that there's some other identities. Cos squared, you do a little bit of rearranging with that double angle and so on. We get 1/2 1 plus cos 2x. And sine squared 1/2 1 minus cos 2x. You remember those from the double angle? No. Okay. Let's write out the double angle. So cos 2x is cos squared minus sine squared. And then you substitute that first equation. So that last one there with the cos 2x, you substitute equation 1 for either cos squared or sine squared, and then you'll get those two. Okay, maybe I should put that for homework. So homework, we've got equation 1, equation 2. Substitute equation 1 into equation 2 and derive those middle two. Okay, you have to know these for these antiderivatives here. Okay, because later on we're going to be working with sine cubed and sine to the 4. We're going to need those identities. Okay. So here we're going to rewrite this. This is going to be 1/2 1 minus cos 2x. A little bit of rearranging. And now we know what to do. We know how to work with the half. We know how to work with cos. We can put down the answer. Okay, antiderivative of cos. Yeah, don't worry about the 2, just the cos. Is sine. Yeah, please don't mix up the minuses. Yeah, so it's sine. But we got the 2 there. If this was the derivative, you multiply by 2, antiderivative you divide. It's always the opposite. So this is going to be minus 1/4, sine 2x. What are we missing? Plus c. Good. Sorry? 1 point. Yeah, you get 1 point if you just write plus c. Yeah. Okay, so problem for homework, and then we'll be done. Yeah. Sine to the 4. So here, you can think of this as sine squared squared. So you can use the trig identity once for sine squared, You use the identity again for sine squared, and then you can get your answer. Okay. And later on, we'll see what happens with sine to the 6 and 8 and all those ones. Right. Any questions about what we covered today? All good? Okay. Please make sure you finish that table for the next lecture. Okay, we will be needing that.